What's that? Oh, it's coming from my camera. Can we use this?
Oh, there you go. Better quality.
Looks like it's working now.
Yeah, sorry, recording. We started.
Let me join.
Yeah, if somebody could be logged onto the Zoom to monitor the chat, like Justin or is Kai coming? I know. They'll do that on the phone.
Not able to share. So next year's screen.
Oh, I need to share that screen on Zoom.
Very nice. Yeah, Sharon.
I need to share the screen.
Okay.
Yeah.
Do we want to hear people from the outside?
I don't think so.
Well, actually, your laptop's already hooked up, so if you're on Zoom, that'll be coming through unless you mute your speakers.
Screen. This one.
There you go.
Okay. Now,
And we can see you.
good.
Can you hear him?
Hello, hello, hello. At the beep. Okay, I think we're set up.
Thank you. Bye.
Recording. Looking sharp there, Matt.
Yeah.
Okay, shall we? All right, good day, everyone. It's my pleasure to introduce our speaker for today. It's our own faculty member here in physics and a member of Institute for Quantum Studies, Matthew Leifer. Matthew is an expert in quantum foundations. He's written extensively on this topic, and I can't think of a better person to talk about this year's Nobel Prize in Physics, and Matt will tell you all about it. So let's welcome Matt Leifer.
Thanks, Andrew. I'm really not used to standing in one place when I give a lecture. We have a Zoom room on with this camera. So I apologize to the people on Zoom if I move away at some point, because that's naturally what I'll do. So I want to tell you about this year's Nobel Prize in Physics. And it was won by these three guys. So Alain Aspect, John Clauser and Anton Zeilinger, and the citation says that they were awarded it for their experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Now, when we talk about quantum physics, especially to a popular audience, people often get a little bit scared. They think it's too difficult for them, or they think it's very confusing. And we're not helped with that because almost every popular talk on quantum physics that I've ever seen has at least one of these quotes in, right? So Richard Feynman says, "I think I can safely say that nobody understands quantum mechanics." Niels Spoor, one of the founders of quantum mechanics, says, "Anyone who's not shocked by quantum theory has not understood it." But here at Chapman, it's our job to understand it, right? We are probably the only research group in the whole United States who really has a significant number of people devoted to understanding it. So I want you to forget all of that, forget that scare nonsense, and we're going to keep calm and learn quantum physics. Now, you probably have heard some confusing things in popular talks or popular science books before. And I want to say that that's because of the uncertainty principle. So has everybody here heard of the uncertainty principle? No, quite a few people. Not Heisenberg's uncertainty principle, though. This is Leifer's uncertainty principle. And what that says is that whenever a physicist tells you about something about quantum physics, there is a lot more uncertainty about it than that person makes out. Okay, so we're in a situation where we have quantum physics. We don't really know what it says about the nature of reality. What is the reality described by quantum physics? And a lot of those questions, we have various possibilities, but we don't know the answer to. There's uncertainty, and that's the normal situation in science, right? There are questions that we have uncertainty about, and we try to investigate them by the scientific method, by thinking rationally about it, deriving theorems mathematically, doing experimental tests, things like that. And this is exactly what happened in these experiments that won the Nobel Prize. So I'm going to start the story back with these two guys, Niels Spoor and Albert Einstein. You probably heard of Einstein. Einstein is most famous for the theory of general relativity, special and general relativity, but they were both, in fact, early founders of quantum mechanics. So they're both involved from the early 1900s in the development of quantum mechanics. Quantum mechanics, as we know it today, took its final form in the 1920s, in about 1925, with the papers of Heisenberg and Schrödinger, left us with the final form of quantum mechanics that we use today. Now, Einstein was unhappy with this. He was unhappy with what ended up being quantum mechanics. He had some problems with it, and he engaged in a famous series of debates with Niels Spoor. And the consensus in the physics community until about the 1990s was that Niels Spoor had won these debates, right? And Einstein was just wrong. Modern scholars have started to reevaluate that starting from the 1990s. And it certainly looks to me like Einstein was correct, at least given the evidence that he had at the time, okay? Given the evidence he had at the time. Later on, we'll have more evidence which might support Bohr's view. Okay, so the culmination of these debates was what's called the Einstein-Podolsky-Rosen argument. And this came out in the paper in 1935. So Einstein, Podolsky, and Rosen published a paper, and then pretty soon afterwards, Niels Bohr published a reply. One of the interesting things about this is that the result was announced in the New York Times, the front page of the New York Times, in fact, before the actual journal article came out. And this was due to the promotion efforts of Boris Podolsky, who was the junior colleague at the time, and was very excited about the fact that he was working with Einstein and talked to journalists about it. Einstein was not very happy about that. Okay, so what I want to do in the next little bit is give you a simple version of the EPR argument. Okay, so this is going to involve three characters. Here we have Alice. This is Alice in Wonderland, one of the original sketches from Alice in Wonderland. This is Bob. That's Bob Marley. So, by the way, the reason why it's Alice and Bob is because it's A, B. So we like to name our characters A, B, C, etc. This here is David Blaine, though. He's a magician, and he's going to do a magic trick. So, in this explanation, David Blaine is going to outline what conventional quantum mechanics says goes on. And Alice and Bob here are going to represent the more skeptical view of Einstein. So the things that Alice and Bob say, you can think of that as basically Einstein's argument. So it starts with David Blaine saying, I'm going to do a magic trick. Okay, so first of all, Alice is going to fly to Venus and Bob is going to fly to Mars. They want them to be very far apart from each other. When they get there, he's going to send them a package. And when they open the package, they'll be amazed. So here we are. Alice has flown to Venus, Bob has flown to Mars, and David Blaine's telling them to open their boxes, and they're going to open their boxes at the exact same time. Okay, so there will be no time for any physical influence to propagate from Alice's box to Bob's box and vice versa, because they're very far apart, and Einstein's relativity tells us that no influences can travel faster than the speed of light. Okay, so they open their boxes, and ta-da, both balls are the same color. They're both red. Now, Bob says, well, he's not impressed. He can do the same trick with Amazon. Let's suppose we have interplanetary Amazon at this stage. You just order two red balls to be sent to two different addresses. And right from the beginning, in the same warehouse, when they started in the same warehouse, it was decided that they were going to be the same color. So the balls have been the same color since they were back on Earth. And so it's no surprise that that correlation is revealed when they open the boxes. Okay, so this isn't particularly impressive to Alice and Bob. So now David says, well, okay, let's do the same trick again. And I guarantee you're going to be impressed this time. So what does he do? They open the boxes again, and this time both balls are blue. And so if you do this experiment multiple times, you'll find that you know, roughly half the time you'll get 2 blue balls and half the time you'll get 2 red balls. And that's it, right? But this isn't surprising either, because it's like, okay, sometimes there's somebody on Earth who just flips a coin, and if they get heads, he puts 2 red balls in the boxes. If he gets tails, he puts two blue balls in the boxes, and nothing surprising going on. No weird non-local effects. Okay, so how about this? Well, so Alice says, well, that's just the same trick again, it's a different color. And now David Blaine says, yes, but not according to quantum mechanics. So he says, well, yes, but according to quantum mechanics, the balls didn't actually decide whether to be red or blue until you opened the boxes. Before that, they were in some kind of spooky entangled state. I've represented that here. There's some kind of mystical connection between the 2 balls. They're in a state where they're neither red nor blue. The only thing that's known is that they're the same. But still, Bob's ball knew that it had to be blue instantaneously as soon as you opened your box, Alice, okay? So this is what quantum mechanics says is going on in this situation. There just really isn't a fact of the matter about whether the ball is red or blue until the box is opened. And if that's the case, then there is really some weird non-local influence going on, because, you know, if I open the box and see red, well, then that box there over on Mars has to know that it also has to be red. So Alice is clever, and she says, well, let's check that you're right, okay? So she has her friend back on Earth, the Mad Hatter. So she says, let's do the whole thing again, and she'll have the Mad Hatter check that the balls really aren't red or blue already by opening the packages before they leave Earth, right? So she wants the Mad Hatter to open the packages and see indeed something like this, that there's nothing in the boxes that would tell you whether the balls are going to be red or blue. Okay, so if you could do that, things would be great, but David Blaine says, well, no, if you do that, then the delicate entanglement will be destroyed. And of course, the Mad Hatter will find either 2 red balls or 2 blue balls, right? But I say it's still spooky because quantum mechanics guarantees that it is spooky, right? They really aren't red or blue until someone looks. And Bob just said, well, why should we believe you? By far the simpler explanation here is that there really were 2 red balls or 2 blue balls right at the beginning on Earth. Or even if they weren't, at least the information about whether it was going to be red or blue was contained inside the boxes from the beginning, right? So maybe the balls do change color, but there's a little message, there's a little computer program inside the box that's going to make sure that they're the same color when they get far apart, and that color is pre-decided. Just so long as the information about whether the balls are going to be blue or red is contained in the boxes from the beginning, then there's nothing spooky or non-local going on. And sure, of course, this is by far the more reasonable explanation of what's going on, and that's what Einstein thought was going on. So this is why he said quantum mechanics was incomplete, because quantum mechanics doesn't say whether the balls are going to be red or blue, but it must be the case if you want a local account of the experiment that there is a fact of the matter about which is going to happen. So most people think, however, that Bohr won this argument, at least they used to think that. Bohr wrote a paper in response, and this is what he said about the supposed non-locality. So I'm going to read this first part to you. Of course, there isn't a case like that just considered. No question of a mechanical disturbance of the system under investigation during the last critical stage of the procedure. But even at this stage, there is essentially a question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. And that's basically what won the argument. I mean, I assume that not many people actually read this paper at the time. And more ink has probably been spilled over what this response means in the philosophy of quantum mechanics literature than possibly any other sentence. But at least here we can sort of say, well, Einstein's argument makes a lot of sense, and this just seems to be extremely ambiguous. So that's kind of where things stood for a long time, until this fellow came along. So the next participant in our story is John Bell. He was a Northern Irish physicist and he shared Einstein's concerns about quantum mechanics. However, between the time of Einstein and Bohr and the 1960s, the attitude in physics had changed quite radically. Physics had become a much more pragmatic subject, right? You have to remember the Second World War happened. So the center of the locus, the center of physics had moved from Europe to the United States. And also physicists have been involved in producing nuclear weapons for the first time, the Manhattan Project. And so everybody was very concerned with the implications of physics, the practical applications, and all of this sort of philosophy and foundations talk really fell out of fashion and was discouraged. So Bell knew that it would be career suicide to work on the foundations of quantum mechanics at the time. So instead, he became a successful particle physicist. It was also a very interesting subject. He worked for a while at CERN, which is the big particle accelerator in Geneva. And he was very well known as a particle physicist and a specialist in the design of accelerators, particle accelerators. So that's what he was known for. But in 1964, he happened to be on sabbatical, and he went to various universities in the US. He went to Stanford, University of Madison, Wisconsin, and Brandeis University. And when he was at Brandeis, he used the opportunity to spend some time thinking about the foundations of quantum mechanics. So he already knew about the EPR argument. So the Einstein-Bohr debates were very famous. So he knew about that. But the other thing he knew about is that von Neumann had an argument that said that it was impossible to complete quantum mechanics in the way that Einstein suggested. There's no way that it's possible that the balls are already red or already blue, right? So anybody who sort of questioned this was usually referred to von Neumann. Von Neumann's shown it's impossible, they would be told. This was published in a book that von Neumann published on the foundations of quantum mechanics in 1932. The book was written in German, and in 1935, a female physicist called Greta Hermann challenged the assumptions of the proof. She said, this is unreasonable, and actually, if you drop these assumptions, it's perfectly fine. That paper was ignored, and von Neumann's argument was only available in German until 1955. In 1955, Princeton University Press published a translation into English, and Bell finally read this translation in 1964 when he was doing this work. So he read it, and he also realized the same thing as Greta Hermann. He published his own paper refuting von Neumann's proof. He also knew of David Bohm's 1952 work, in which he had constructed a completion of quantum mechanics, which you might say is along the lines of what Einstein wanted. So it was a theory in which quantum particles had a definite position, a definite trajectory at all times, in violation of uncertainty, the idea that there's fundamental uncertainty. Bell said of this work, I had seen the impossible done. So he then looked into von Neumann's proof, noticed that there were flaws in it. The other thing he noticed, however, was that Bohm's theory involved instantaneous action at a distance. Okay, if you change something over here, then something might immediately change very, very far away. So that would be in conflict with the speed limits of relativity. So he wondered to himself, is it necessary that any theory that reproduces quantum mechanics must have these faster than light influences? And he came up with a proof that indeed it would. Any completion of quantum mechanics would involve faster than light influences. That's what we're going to talk about. He didn't publish this in any mainstream physics journal, such as the Physical Review journals. That would have been the natural place to put it, because he was embarrassed to ask his hosts at Brandeis to pay for the page fees. So back then, those journals charged you to publish in them. He didn't want to ask his hosts to pay for this crazy paper about the foundations of quantum mechanics, which was still a very marginal subject. So instead, he published this in a new journal, which was called simply Physics. And that journal paid authors for articles. So that seemed a good solution to him. However, that journal folded after only very few issues, and hence the paper was pretty obscure for several years. Okay, so nobody did anything. Okay, so the next chapter is these guys, Clauser, Horn, Shimony, and Holt. And here's the first of our Nobel laureates, John Clauser here. So let's start with Clauser. So in 1967, Clauser was a PhD student at the Goddard Space Institute. And he's in a library randomly looking at papers. That's something that I used to do when I was a graduate student, but because everything's online now, people don't randomly look at journal articles in libraries. It's a shame. And he happened to stumble on this physics journal, and he saw John Bell's article. He read it, and he was immediately hooked. And he began to think about whether it would be possible to experimentally test the result of John Bell. The problem with Bell's original proof was it required that you could observe these perfect correlations, right? So you would always see, if you measured in a certain way, you would always see definitely red, red, or definitely blue, blue. If you have any experimental imperfections, and you sometimes see red, blue, any slight bit of noise at all would destroy that original argument. But Clauser thought he might be able to come up with a more robust argument that didn't require that, and then experimentally test it. So independently, this guy, Abner Shimony, found out about Bell's theorem. He found out about it because John Bell sent him a copy of the paper. Shimony was one of the few people around who was working on the foundations of quantum mechanics. He had PhDs in both physics and philosophy. And if you're a philosopher, it's always been allowed to think about the foundations of quantum mechanics. So he was at MIT at the time, and he was even taught a course on the foundations of quantum mechanics. So he was well known. It was well known that he was interested in this subject, and that's why John Bell sent him the paper. So Shimony was also interested, and he got together with his graduate student, Michael Horn, to try and think about experimental tests. So in 1969, Clauser submitted an abstract about experimental tests of Bell's theorem to the American Physical Society meeting. This is the largest meeting of physicists, well, in the world, in the States anyway. And so Shimony was browsing the abstracts, and he saw this. And he thought, oh dear, we've been scooped. What should I do? So what he did was he went to Eugene Wigner, who was his PhD advisor in physics, and asked him for his advice. And he said, well, why don't you try and collaborate with this guy, find out who he is rather than competing with him. That's what they agreed to do. They met up at the meeting, and they discussed experimental tests. By this time, Shimony had also involved a guy called Richard Holt, who was another PhD student, but he was an experimentalist, right? And he was working at Harvard. And this was the guy who Shimony thought would do the experiment for him. Okay, so these four were getting together and discussing, and they eventually came up with a version of Bell's theorem which could be robustly experimentally tested. And I want to explain that to you now. Okay, it's also the simplest version of Bell's theorem. Okay, so we're now going to switch gears and explain what's called the CHSH game. So I can explain in the form of a game exactly what this result is about, and then I will afterwards explain what it has to do with quantum mechanics. So in this game, there are 4 participants. Really, we're going to have Alice and Bob here. They're going to play the game, and Charlie and Dora are there to act as referees. Okay, they're just there to make sure that everything's fair. I never know if my pop culture references are too sophisticated for the audience. This is one that's Charlie Chaplin, and I presume you probably know that one. That's more likely. Not Pavel, because he's from Poland. That's Dora the Explorer, which is a cartoon. Anyway, so here's the game. So this is the most complicated slide in the entire talk. If you understand this, you'll get everything else. So here's the game they're going to play. So first of all, Alice and Bob, they get together and they're allowed to have a few minutes, or as long as they like really, to discuss their strategy for how they're going to play the game. During this time, they're allowed to do anything. They can talk to each other. They can generate random numbers. They can throw dice and things like that to generate random numbers if they think that will be useful to them. They can just talk about how they're going to play the game, etc. Then Bob is going to leave the room with Dora. Alice and Charlie is going to stay where they are. From this point onwards, there is no communication between the Alice-Charlie pair and the Bob-Dora pair. No communication whatsoever. They're not allowed to talk to each other. Now, Charlie and Dora each have a coin. So they each flip a coin and write down the outcome of the coin flip, heads or tails. And Alice and Bob have to write down either red or blue in response. Okay? So here are the conditions for how Alice and Bob can win the game. If the two coin flips are either heads, 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 tails, or tails, heads, then they will win that round if they happen to say the same color. Either they both say red or they both say blue. If the coin flip is tails, tails, on the other hand, then they win if they say opposite colors. So either red, blue, or blue, red. Okay? But they have to do this without communicating. So then we repeat steps 3 to 5 many, many, many times to generate statistics of how many times they can win the game. So then Bob and Dora come back in the room and they count how many times Alice and Bob won, as well as the total number of times they played, and then they can figure out what percentage of times they won the game. And their goal is to try and win the game 85% of the time. Quick poll, does anybody here think they can do it? Yeah, you know the answer. Okay, they can't do that. They can't, in fact, they can only win this game at most 3/4 of the time. And so now I will explain why. Why can't they always win? Okay, so if you look at this diagram here, basically, first of all, I'm going to focus on deterministic strategies. So we're just going to assume that Alice and Bob decide what they would answer for every coin flip right at the beginning. Okay. So Alice needs to know what's going to be her answer if Charlie's coin flip is heads. That's represented by this dot here. If it's tails, this dot here. Similarly for Bob's answers when it's heads or tails. And this network here represents the constraints that we have for the winning conditions. So if there's a solid line, then those two answers are supposed to be the same. And the dotted line means that those two answers are supposed to be different. So let's go and try and fill in this this graph here. Well, we could let's just pick red down here just to start with. It could be either, but let's pick red. Then this line tells us that this answer had better be the same. This line then tells us that this answer had better be the same. And this line tells us that this answer had better be the same. So they're all red. But then you look at this link and you see, oh dear, this one isn't satisfied. So 3 out of the 4 possibilities are satisfied. So with probability 3/4, we'll either get heads, heads, tails, heads, or heads, tails. But if they happen to get tails, tails, they'll lose the game with this strategy. And so you might think, well, let me try and fix it. I'll change that to blue. Okay, now this is satisfied, but now this link isn't satisfied. And it's sort of very easy to see that however you make the assignments, there will always be at least one of these links that isn't satisfied. It's very frustrating when you try and do this, which is why this is called a frustrated network. You cannot satisfy all of the constraints. So that means that for any deterministic strategy, they can win at most 75% or 3/4 of the time. And if you don't believe me, here's the listing of all the possible deterministic strategies, and you can count up how many of the conditions are satisfied, and they all either win 75% of the time or 25% of the time. That's it. Okay, So that's deterministic strategies, but we should also think about, would using randomness help? You know, Alice and Bob could not choose a fixed strategy, but they might use classical randomness, like coin flips, dice throws, or whatever, to choose it each time differently. This doesn't help them either. And the reason it doesn't help them is because Charlie and Dora's coin flips, whatever they're doing with their coin flip, are independent of whatever randomness Alice and Bob are generating. So independent of each other. Now, on each round of the game, they will randomly end up choosing one of the deterministic strategies. It's not fixed in advance which one they'll choose, but they'll choose one of them. And each of them has a winning probability of less than 75%. So the average of the winning probability can't be higher than the winning probability of the best deterministic strategy. So it doesn't help them. They might as well just pick the best deterministic strategy. It doesn't help if there's randomness. The only other thing they could do is they could delay their decision. So Alice and Bob could not decide what they're going to say until they've seen the outcome of the coin flip. So locally, they each have 4 choices of strategy, and basically they could wait till they've seen heads or tails to choose what they're going to do. They could choose the probability that they're going to say red, or the probability that they're going to say blue differently, depending on whether the coin flip is heads or tails. Does this help? This also doesn't help, because the thing is, basically it amounts to generating 2 different kinds of randomness. So there's the randomness I'm going to generate if I see heads, and the randomness I'm going to generate if I see tails. Perhaps you have 2 biased coins with different biases. And this is the one I'm going to flip if I see heads. This is the one I'm going to flip if I see tails. Well, why not take those coins back in time with you all the way back to the beginning of the experiment when Alice and Bob were together, flip both coins and note the answers to both of them. And then when you get over to Charlie or Dora, you just use that sample that you've already generated if it's heads or tails, right? So you can move the randomness right back to the beginning. And if you move the randomness right back to the beginning, it's just another instance of non-deterministic strategies. So it doesn't help. There's a reason why I talked about this, by the way, because this is what a lot of people think happens in quantum mechanics. So remember, when I was talking about the EPR experiment earlier, quantum mechanics says that there's no fact of the matter about whether it's going to be red or blue until it's measured, right? So quantum mechanics says, well, the decision really doesn't get made until then. But that's included in this analysis here. Okay, so with that caveat, we can see that whether they use a deterministic strategy, a non-deterministic strategy, or they delay their choice until they see the coin flip, their outcome probabilities will always satisfy this inequality. So each of the pairs of coin flips will happen with probability 1/4, and then this is the winning probability on those coin flips. Whatever mixture of strategies they choose, that winning probability will be bounded by 3/4. And this is what is called the CHSH inequality, a version of it. Okay, so they can't win with probability more than 3/4. However, if they had been allowed to take a pair of entangled quantum particles with them, they would be able to win with 85% probability. So they can beat this bound. So what's going on? Okay, well, let's look at what the physics behind this really is. So usually these experiments are done with photons, so particles of light, and with photon polarization. And any good physicist should have a couple of polarizers in the pocket. I don't know if you'll be able to see this on Zoom, probably not. So you have, so light, classically light is a wave. Okay, so a wave can be wiggling in various different directions. It can be oscillating up and down, vertically or horizontally. It can be oscillating or at any other angle. Okay, and if we have these polarization filters, what they do is they let through light in one direction and not in the, and they block light in the other direction. Right, so if I take the light from this light, you can see that the light from this screen is actually polarized because it goes through in this direction and not in that direction. Anyway, so if I take this polarizing filter, then it will let through light that's, say, vertically polarized. So if I put another polarizer in front of it that's also oriented in the vertical way, then the light that gets through the first one will also get through the second one. If I put it at 90 degrees so that it's now horizontally oriented, then no light gets through. And if I rotate them, then you can see that you get a gradual transition from one to the other. So what's happening when the polarizers are crossed is at some angle is that, okay, maybe vertically polarized light is coming out this way, but I can decompose that light into its component in this direction and the orthogonal direction. And this part is going to get through the crossed filter. Okay, well, you guys can pass around some polarized filters and play with them. Pass them around. All right, and play with all that. So the goal in these experiments is we want to generate a state of two photons where they're polarized, according to quantum mechanics, their polarizations are the same, but we actually don't know which polarization it is. The state is written down like this: horizontal, horizontal plus vertical, vertical, but that's all it really means. And then we measure those photons polarizations at various angles. The important thing is that in the EPR experiment, you always did the same measurement on both sides of the experiment. To get a violation of the CHSH inequality, you actually have to do slightly rotated measurements. So you're doing different measurements on each side. Now, let's look at the implications of the analysis that we did before. So what's going on here is we have some source of entangled particles. This, by the way, is what's called a space-time diagram. So space here is going right to left and time is going up the page. And what's going on here is that nothing can travel faster than the speed of light according to special relativity. So these dotted lines, the space inside these dotted lines represents everything that can possibly influence B. Okay, so I'm drawing things going at the speed of light at 45 degrees. And so anything inside this, what's called a light cone, can influence B, anything outside of it can't. And similarly over here. So we have a source of entangled particles, one of which goes to Alice and one of which goes to Bob. They're traveling at the speed of light or less. And then on Alice's side of the experiment, we have a coin flip, that's this X here. And that coin flip decides which of two measurements are done over here, and A is the outcome. Similarly over here with Y and B. Now, since by special relativity, these two things here cannot directly influence these two things here, because it would take a signal going faster than the speed of light. If they're correlated, if the two measurement outcomes are correlated, it must be because of their common past. So we take some region, it's called a screening off region, such that any influence from the entangled parts, from the source of entangled particles to A and B must pass through this region. And we call this thing lambda here is supposed to be just a complete description of everything that physically exists in that region. We don't really necessarily know what that is, but let's just say such a thing exists. Then given lambda, lambda must contain all the information about the correlations that exist between A and B. And the choice of lambda is really exactly the same thing as the choice of strategy that Alice and Bob had to play the game earlier. That's what lambda really is. It can be random. It can involve only, it can say, do different things depending on the coin flips up there. But basically, since it's responsible for all of the correlations between A and B, this is just like picking a strategy. And so the argument here applies that the correlations between A and B should be such that they can only win the game 3/4 of the time. Okay, but in quantum mechanics, we win it more than 3/4 of the time. Okay, so that means that according to this diagram, there must be some kind of non-local influence, perhaps from here to here. Okay, if Bob's answer is allowed to depend on Charlie's coin flip, then we could reproduce the experiment, for instance. Okay, so let me talk about experimental tests, at least briefly. So Clauser was the first to consider doing experimental tests. And here's a quote from him. I just want to illustrate the atmosphere that was not in favor of doing experiments in quantum foundations at the time. So he says, while I was performing the 1972 Friedman and Clauser experiment at UC Berkeley, Friedman, by the way, was his graduate student at the time, Caltech's Richard Feynman was highly offended by my impertinent effort and told me that it was tantamount to professing a disbelief in quantum physics. He arrogantly insisted that quantum mechanics is obviously correct and needs no further testing. Okay, so that's the kind of atmosphere he was working in. So anyway, he did this experiment. He found some professors who were willing to sort of shield him and give him equipment to use. So what was happening in this experiment is, you see, you have two wings here. This is Alice and Bob, separated from each other. In the middle here, he generates pairs of entangled photons using what's called a Cesium Cascade. So you have a cesium atom that's in one of its excited states, and it drops down to a low energy state, and then it drops down again. Each time it emits a photon. And the way that that cascade happens, the conservation of angular momentum means that the two photons must have correlated polarizations, okay, entangled polarizations. Now, these two photons might come out in any old direction, and he needs one of them to go here and one of them to go there. And that will happen randomly occasionally, but it'll take a long time to generate a pair that will go in the right direction. Okay, now when they go, one of the photons goes down here, the other one goes down here. He has a polarizing filter and then a detector, so he can detect whether the photon, what polarization the photon had in the correct directions. So he did this experiment and he found the violation of the Bell inequalities, the violation of the CHSH inequalities, confirming quantum mechanics and sort of ruling out these local descriptions. However, at the same time, Holt, remember him, Richard Holt, he did an experiment with his advisor at Harvard, a physicist named Pipkin, same sort of experiment, and they failed to show any violation. So for a while, there's controversy about whether the inequalities were violated or not. So there was a series of experiments done between 72 and 75 with Clauser, that Clauser's results were replicated many times, and the Holt and Pipkin experiment was never replicated. So eventually that won the day. Okay, and we're low on time, but let me talk a little bit more about the experiments. So that wasn't the end of the story because of what are called loopholes. So there are two loopholes in these experiments. So they're called the detection loophole and the locality loophole. So the detection loophole says, well, if not all the particles are detected, then they might preferentially choose not to answer inconvenient questions. And think about this. Imagine Alice and Bob are playing the game, and imagine that any time Charlie did a tails, Alice, instead of answering, was allowed to disappear, right? And then we just don't count those runs. Okay, we don't count the other runs. Well, if that were the case, then they could win the game all the time because, you know, they would only ever have to deal with heads, tails, or heads, heads, two possibilities. Okay, so if you have, you can do things more sophisticated than that, but the point is that if you lose a significant proportion of your runs of the experiment, then you could imagine that this is exploited in order to win the game. And indeed, photon detection was very, very bad in those days, and almost all of the photons are lost in this experiment. So it's really open to this loophole. There's also the locality loophole, which says that, you know, if you don't change your measurement settings fast enough, then there'll be time for a signal to propagate between the two wings of the experiment, right? So here, these settings need to be chosen in such a way that there's no time for a signal to go from here or here. And that requires you to do them very, very fast, especially in an experiment. This experiment you can see is only like less than 10 meters long, right? And so the speed at which you go switch the settings would be horrendously fast. And of course, they didn't do that. They just switched the settings slowly. Okay, so at that point, people realized that there were these loopholes. So then Alain Aspect, our next Nobel laureate, comes onto the scene. I couldn't find a picture of his lab, by the way. So this is just one of the diagrams from his paper. So he's a French physicist with a very impressive moustache. He was at the École Supérieure d'Optique in Orsay, and he was about to do his PhD. So he was already a physics instructor, a lecturer. He had a lectureship, but he didn't have a PhD yet. So a colleague told him about a talk that Shimoni had given about Bell's theorem. And so he looked up the papers and got interested. He looked up Clauser's papers. It was like, well, I don't want to just repeat the experiment. Can I find something interesting to do? So what he did was he went to visit John Bell at CERN in about 1980. And what he did was he asked John Bell, is there an interesting experiment I can do? And John Bell turned to him and said, do you have a permanent job? Because at the time, it was still considered career suicide to work on these things. And he said, yes, I do. I have this lectureship. And Bell said, okay, fine. You should try and close the locality loophole, basically. So he made a few modifications to the Clauser type of experiment. So here, instead of using these polarizing filters like I handed out, he used what's called a polarizing beam splitter. That means that instead of absorbing photons, half of them go one way. Well, they go down one of two different channels. And so therefore you could, in principle, detect all of the photons if you had good enough detectors. And the other thing he did was he changed the settings quickly. So the way he changed the settings quickly was not by rotating these great big macroscopic things, but by having two of them. So he had one set at one angle, another one set at the other angle. And then he used a switch, a piezoelectric switch, to direct the photons either down one channel or another channel to one of the two polarizers. So unfortunately, he didn't quite close the locality loophole, because although he definitely improved on Clauser's experiment, the measurement settings were not changed randomly, but they were changed in a periodic fashion, in a pattern. And of course, the other wing of the experiment could in principle know about that pattern and exploit that. But the other thing that he did that was very important was that he popularized the experiments. Now, although it was difficult to interest physicists in the foundations of quantum mechanics at the time, it wasn't so difficult to like say, here's an interesting experiment, look at these interesting correlations. And Aspect knew how to do that and talk to physicists. So post Alain Aspect, the amount of interest in this area increased quite rapidly, and it became less of a stigma to work on it. Okay, so then we come to Anton Zeilinger, our third Nobel laureate. He has for a long time wanted to close the loopholes. Okay, so he improved the experiments vastly. So in 1998, he was at the University of Innsbruck, and he closed the locality loophole for photons. The way he did this was they used what's called a quantum random number generator to choose the settings. This is like you have a photon that goes into a beam splitter, and you detect whether it comes out one way or another. And this is supposed to be completely random according to quantum mechanics. And he used that to very rapidly switch the settings, and he had his two wings far enough away that he managed to close the locality loophole. He then was working on closing the detection loophole, and he did it in two different ways. So first of all, the first way he did it, also in the late 90s, was instead of using photons, to use ions, which are atoms which have either lost or got extra electrons, so charged versions of atoms. They can be trapped electromagnetically close to one another. He was able to entangle them and do the Bell experiment. And of course, that closed the detection loophole because photons Light doesn't really like to interact with things very much. That's why one of the reasons why it's hard to detect. It's one of the reasons why I can see you so well. Light doesn't get disrupted by flying through the air, just comes straight towards me. So it's hard to detect, but atoms, they're easier. They're not going anywhere. It's easier to detect their states. So he closed the detection loophole in that experiment, but those atoms, those ions, were very, very close together. No chance of closing the locality loophole in that experiment. Eventually in 2013, Zeilinger's group closed the detection loophole with photons. And they didn't do anything fancy. They just, technologically, photon detectors got better over time. New techniques, solid state physics, etc. By that time, they were good enough, but it was only good enough if the two wings of the experiment were quite near each other. So it didn't close the locality loophole in that experiment. As you move the two wings apart, photons are going to get lost for other reasons, right? They just like, if you have a photon going through an optical fiber, sometimes they'll get absorbed by something along the way. So if you move the things further apart, your detection probability is going to go down, and he wasn't able to close the detection loophole in that experiment, the locality loophole in that experiment. So at that point, the race was really on to get a loophole-free test, especially since 2014 was the 50th anniversary of Bell's original paper. So everybody was trying to do a loophole-free test in that year. It didn't happen in 2014, it happened in 2015. And the first people to do it were actually these two, not any of the Nobel laureates. That's a group of Ronald Hansen in Delft in the Netherlands. They did a very, very clever experiment, which involved, I don't have time to get into the explanation, but it involved what are called nitrogen vacancies in diamond, and a very clever way of entangling those. And they managed to close both loopholes. Their experiment took ages, though. It took ages for them to entangle things, and they had to run the experiment for like 2 weeks to get like 200 data points or something like that. Their experiments were followed very quickly, within a matter of weeks, by Zeilinger's group in Vienna, and also a group here in the States from the National Institute of Science and Technology, doing experiments with photons, the original kind of experiment, finally closing both loopholes in the experiment. So I was going to talk a little bit about practical applications of this, but since time is low, I'm going to skip that. What I want to say is something about, what does this say about the nature of reality described by quantum mechanics? What can we say in light of Bell's theorem? Well, here are 4 possibilities. One is we could accept that there are non-local influences in nature. And for example, Bohm's theory, which I mentioned earlier, does that, okay? We could have multiple worlds. Now, there is a many worlds interpretation of quantum mechanics that a significant number of people believe in. So one of the assumptions that goes into Bell's theorem, of course, is that experiments have single unique outcomes. If you start saying, actually, all of the outcomes of an experiment happen, then you get around the reasoning in Bell's theorem. We could also have, so one of the assumptions of Bell's theorem is that you can make the choices of measurement setting independently of anything else that influences the outcome. You could argue, well, maybe that's not true. And one way that could be not true is if there are influences that go backwards in time. So the choice of measurement settings could influence something earlier, or just if there are sort of correlations between the two have been set up sometime in the past. So these are not very popular theories, but they do exist as a possibility. The most popular option, though, the one which corresponds to the standard Copenhagen interpretation of quantum mechanics, is simply to deny that all correlations need to have causal explanations. So what does that mean? If I go back to this diagram here, we see that we're trying to here generate a causal account, right? So this lambda here in this blue region is supposed to be the cause of the correlations between Alice and Bob. And if you believe in the Copenhagen interpretation, you'll just say, well, some correlations don't have causes, they just are, okay? And one of the ways you can justify that is you can say that although we have this sort of proof of Bell's theorem and the non-locality, you cannot, in fact, use these correlations generated from entangled states to send a signal. Alice and Bob can't send a signal to one another with an entangled state. So you could take the position that there's only a cause. I'll only say something is a cause of something else if it would be possible to send a message from here to here. And that's not the case with these entangled states. So, you know, personally, I'm not a big fan of that, but it is an option. So I just wanted to let you know. So finally, I just want to say, like, the most important thing that we learned from Bell's theorem, as far as I'm concerned, is not necessarily about entanglement or non-locality, but it's just that if you have a conceptual question about your physical theory, then you can approach this rigorously. You can actually formulate things precisely. You can write down mathematical assumptions about your theory, and you can then do an experiment. And this is the methodology that I like to follow in my work on quantum foundations, to try and turn these conceptual questions into real physical theorems and experiments that we can do. So I'll leave it there. Thank you.
Thank you, Matt. We have a few minutes for questions, especially from the students that are hearing about this for the first time. But maybe I'll get us started to kind of break the ice and warm myself a little bit.
Yeah.
So if I go back to your Amazon shipping factory, the blue balls and the red balls. So if I replace those with the photons, does this really tell me that I cannot describe these as either red balls or blue balls? Is that one of the messages of the violation of inequality?
Well, the message, not that you can't, but if you did, you would have to admit that you would still have to admit that there were non-local influences, right? So Einstein's idea was that by saying that we have red or blue from the beginning, we would be able to get rid of the apparent non-locality. But Bell's theorem tells us that no, even if you have that, even if you complete quantum mechanics in some way, you still have to have a non-local influence.
So either I have to give up locality or give up this reality in some sense.
See, my take is it's not really giving up. Like, I know that a lot of people like to say, okay, the assumptions of Bell's theorem are locality and realism. So either you give up locality or you give up realism. I don't know what that's supposed to mean. So the realism part, for me, I mean, there are various ways of formulating Bell's theorem, but for me, the only thing that realism is doing is this here, saying that we need to have a causal explanation of correlations. So really, you know, if you're giving up realism, you should really say, I'm giving up on the idea of causal explanation. That's how I would put it. Anybody else over there? Yes.
That means that things happen without causes, like it just spontaneously decides to be
Correct.
of a certain.
You have to say that those correlations just are. You know, they just are, and there isn't. And it's perhaps surprising that that's the mainstream opinion in physics. I mean, it's not necessarily that all physicists realize that that's their opinion, but if you profess the Copenhagen interpretation, then that's really what you have to believe. Any other questions?
So
We've got
one of the deep things about this is that it forces you to examine your beliefs about how the world works, and says that something in your belief system is wrong because it does not square with the experimental reality. So we have to sort of decide what we're willing to part with. Right? And that's really something quite profound. I think that's why it's such an important discovery.
Apparently there is a question on the Zoom, Jesse.
Yeah, hi. Thank you for this very interesting presentation. There was a slide that mentioned that talked about if it was almost like if the quantum particles don't know that they're being observed or something. I don't know. It was like a slide. Could you just explain that slide one more time, or that section? They won't bother. I don't know. I didn't really understand that. I was reading that over and over. And
you'll have to tell me where it is.
Oh, there it is. There it is. Right here.
Right here?
The next one after this.
This one?
No, we just passed it. Right here, yeah,
All right,
this.
okay.
If all the quantum, yeah,
Can
this
you
one.
repeat the question, please?
So
Yeah.
you want to you're asking for an explanation of the detection loophole, is that right?
Yeah, exactly. Yeah, and maybe the locality as well, if you can.
Yeah, okay. So I mean, the thing is, exploiting these loopholes isn't necessarily likely, right? But we're trying to rule out any possibility of a local description. And so you might be prepared to contemplate some quite strange theories in order to preserve locality. So the point is that in any real experiment, when I shoot a pair of photons out to two wings of the experiment, sometimes those photons will just get lost and there'll be no detection. Photon detectors aren't perfect. The photons might get lost along the way, etc. So you can imagine a theory in which whether or not a photon gets lost is correlated with the outcome of the coin flip. Okay, so in any deterministic strategy, there's one pair of coin flips that's going to cause them to lose. Let's say it's tails, tails. Well, you could arrange it so that if the particle going to Alice sees tails, then it says, "Oh, I'm just not going to, I'm going to disappear. I'm not going to get detected." And then for the other two possibilities, which are like heads, tails, and heads, heads, they would win. Okay, and then if you don't count those cases where the particles disappear in your statistics, if you just say, "Oh, let's just throw that data out," then you will conclude that they could win 100% of the time. So you have to be careful about things like that. So actually, in order to rule that out for the CHSH inequality, you need your detection efficiency to be higher than 82%. There are other inequalities where it's lower, but you need the kind of efficiency you need is at least something like 2/3 for any known Bell test that we can do. Does that help?
Yeah, thank you so much.
Okay, any other questions? Up in the back.
Can you suggest a book if an interested undergraduate would want to explore this further?
Oh dear. Suggest a book. Okay. Well, it depends if you're interested in getting more into physics, or you just want things at a popular level. Like if you're going to study foundations of physics as a subject, then you have to at some point read the collection of John Bell's papers, which is called Speakable and Unspeakable in Quantum Physics. Everybody who researches quantum foundations should read through that book at one point during their career. If you want a popular science book, I have to say they're all pretty bad. Adam Becker, yes, Adam Becker's book is good on the history of this. So if you want many more details of the history, there's a book called What is Real by Adam Becker. He's visited here before and given talks here. So that's a good book on the history. A book that gets the physics right, 100% right, that's harder to nail down a popular level book. I kind of like How to Teach Quantum Physics to Your Dog by Chad Ozell. I think he's done a reasonably good job of explaining things. But, there's no book that's perfect.
Okay, let's thank Matt again for this nice talk.
Thank you.